Module 2, Lecture A, Lists and Tuples. By the end of this lecture, you will be able to create lists and tuples to store ordered chemical engineering data, access and transform sequence elements using indexing, slicing, and loops, and summarize measurement sequences using built-in operations and functions. Ordered chemical data, temperature lists. In chemical engineering, temperature data often represents a sequence, such as readings over time, along equipment, or across process stages. The order of these values matters because it shows how the process changes, such as heating progress in a batch reactor. In programming, using a list preserves that order so the data continues to match the physical process accurately. A temperature list organizes related measurements as one ordered set instead of separate values. This makes it easier to track changes over time or compare conditions such as inlet and outlet temperatures. Because the values stay in sequence, they can reveal trends, gradients, and delays that unordered data might hide. When creating temperature lists, keep the data consistent and meaningful. Use one temperature scale throughout and know what each list position represents, such as a time step or a sensor location. The order of values gives the list its meaning, allowing engineers to compare runs, find anomalies, and calculate key measures like minimum and maximum temperatures. Python code. Temperature lists. Temperature lists keep process measurements in order, where each position reflects a meaningful condition. Built-in functions can then summarize these small sequences safely and simply. We create a list to store reactor temperatures measured in degrees Celsius. The values represent readings from different times or stages of operation, making it possible to track how the temperature changes over the process. A list of time intervals in minutes is used to match each reactor temperature reading with its measurement time. This keeps the data in the correct order and supports accurate analysis. Check that the Celsius temperature readings and time values contain the same number of entries. If they do, each temperature matches a specific time, so the data sequence is properly aligned and can be considered valid. To understand the temperature range of the process, use the first temperature reading as the starting value and the last reading as the ending value. Together, these values show how the temperature changed over the full measurement period. Slicing is used here to take the middle portion of the temperature list. By selecting the readings from index 1 through 3, it leaves out the first and last values and focuses on the main heating phase. To summarize a temperature list, find the lowest value with the minimum function and the highest value with the maximum function. Then calculate the average by adding all the temperatures and dividing by the number of entries. Together, these values show the range and overall trend of the temperatures. The output checks that the time and temperature data are aligned, then shows the temperature readings in Celsius. It highlights the first and last readings, extracts the middle values to focus on the heating period, and summarizes the data with the minimum, maximum, and rounded average temperature. Finally, it pairs each time with its matching temperature to show the process history in order. The script analyzes reactor temperature readings matched with times in minutes. It first confirms that both lists have the same length, then reports the starting, ending, and middle temperatures. It also calculates the minimum, maximum, and average temperature, rounded to 1 decimal place. Finally, it prints the results along with the time and temperature pairs to summarize the process history. Creating ordered sequences. In chemical engineering, the order of data matters because measurements such as temperatures or pressures often follow a time sequence or physical path. Lists and tuples help preserve that order, so each value keeps its intended meaning. This makes it easier for engineers to organize raw observations before analysis or comparison. Choose between a list and a tuple, based on whether the ordered data should change. Use a list for data you may add to, update, or reorganize, such as experiment readings. Use a tuple for fixed records, such as mixture components or specimen dimensions. This choice helps communicate whether the data is flexible or meant to remain stable. Ordered sequences help chemical engineers keep related measurements matched to the way an experiment unfolds. In studies such as reactors or heat exchangers, values like time, temperature, concentration, flow rate, and pressure drop must stay aligned so the data remains consistent. Careful organization from the start makes later analysis more reliable and keeps the physical meaning of the data clear. Python code, creating ordered sequences. Use lists for measurements or data that may change, and use tuples for fixed records that should not be altered. In both cases, the order of items matters because it carries engineering meaning. We create a list to store reactor temperature readings in Celsius. It begins with 4 decimal values, and a list is appropriate because the readings can be changed or extended as new measurements are collected. A new reactor temperature reading is added to the end of the existing list using the append method. This keeps the readings in the order they were collected, which helps preserve the timeline for later trend analysis. The first recorded reactor temperature is being corrected to 82.4 degrees Celsius. This update accounts for a calibration issue and keeps the temperature data accurate. A tuple is used to store the chemical components ethanol and water in a fixed order. Because tuples cannot be changed after they are created, they help keep the component list consistent and protect its order throughout the program. A tuple is used to store the specimen's 3 centimeter dimensions because those values should stay fixed. Since tuples cannot be changed after they are created, they clearly represent stable, unchanging data better than a list. The code displays 3 ordered data collections in Python: a modifiable list of reactor temperatures, a fixed tuple of mixture components, and a fixed tuple of specimen dimensions. It shows that lists are useful when values may change, while tuples are used for stable, constant sequences. List positions help show how data changes over time. Selecting index 0 gives the first recorded temperature, while selecting -1 gives the most recent temperature. This shows why the order of elements in a list can carry important meaning. To quickly summarize the reactor temperature data, display the first reading, the most recent reading, and the total number of readings. The first and last values show the starting and latest measurements, while the length of the list shows how many temperatures have been recorded. This message explains the key difference between lists and tuples in Python. Lists are flexible and can be changed, while tuples are immutable and keep data in a fixed order. Use lists when data needs to change, and tuples when it should stay stable. This script shows how Python uses lists and tuples to store ordered data. A list of reactor temperatures is changed by adding a reading and correcting another, demonstrating that lists are mutable. Tuples are used for mixture components and specimen dimensions, showing that they keep a fixed order and cannot be changed. The example also uses the order of the temperature list to get the first and last readings and count the total, highlighting that lists are useful for changing data, while tuples are better for stable data. Chemical data containers. In chemical engineering, ordered data containers such as lists and tuples help group related values while preserving their sequence. This is useful for data like reactor temperatures or feed flow rates, where order gives the measurements context. Keeping both the values and their order makes the data easier to analyze, compare, and use in calculations. Lists are useful for data that changes over time because they store related values in an ordered sequence that can grow or be updated. For example, learners can add new experiment readings or sensor measurements as they are collected. This makes lists a practical way to manage dynamic data, such as trial results or calibration readings. Tuples are useful when data should remain fixed after it is created, such as stable dimensions or operating conditions in chemical engineering. They signal that a set of values is finalized, unlike lists, which imply the data may change. Choosing tuples for fixed information supports safer, clearer data handling in calculations and reports. Python code. Chemical data containers. In chemical data, lists are useful for measurements that may change, while tuples are better for fixed records. Both keep their items in order. We create an editable list to store reactor temperature readings. The starting values are measured temperatures, and the list can be updated as new data is added or existing readings change. A new reactor temperature reading, 86.3, is added to the end of the existing temperature list. This keeps the record updated for monitoring or later analysis. A tuple is used to store a pipe's fixed dimensions, its diameter, wall thickness, and length. Because these measurements should not change during the program, a tuple helps keep the data constant and reliable. The pipe geometry tuple is unpacked into separate values for diameter, wall thickness, and length. Giving each measurement a clear name makes the code easier to read and lets those values be used directly in later calculations or processing. To summarize reactor temperature readings, first count how many measurements are in the list. Then find the average by adding all the temperatures and dividing by that count. This mean temperature gives a simple overview of the reactor's overall temperature trend. To compare temperature readings over time, select the first value in the list for the starting measurement and the last value for the most recent measurement. This gives a quick view of how the data changes from beginning to end. The output reviews recorded reactor temperatures and fixed pipe dimensions. It shows the temperature readings, identifies the first and last values, and reports the average temperature rounded to 2 decimal places. It also displays the pipe geometry, including key fixed values such as diameter and length, for quick reference. This script shows how lists and tuples can organize chemical data. Reactor temperatures are stored in a list, so new readings can be added, while pipe dimensions are stored in a tuple to represent fixed values. The script then calculates the average temperature, finds the first and last readings, and prints the updated data with rounded and formatted results. Overall, it demonstrates using lists for changeable data, tuples for fixed records, and basic data processing for output. Sequence access. Indexing elements. Indexing lets you pick one specific item from an ordered sequence, such as a list or tuple. Each item has a position number starting at 0, so the first value is at index 0. This is useful when you need to inspect or compare a particular measurement, such as a temperature, pressure, or concentration at a specific time. Indexing can move from the end of a sequence as well as from the beginning by using negative positions. This is useful when the final item matters, such as the last reading in a dataset or the final condition in a batch process. Always check the size and structure of the data first, because trying to access a position that does not exist will cause an error. Indexing lets you access specific elements in a sequence so you can use them in analysis and decision-making. Lists can be changed when data needs updating or correction, while tuples can be read but not modified. This makes lists better for dynamic data and tuples better for stable records, especially when building clear program logic and engineering contexts. Python code. Indexing elements. Practice working with ordered engineering sequences by indexing their elements. Lists can be both read and changed, while tuples are used when you want data that can be read safely without modification. The code stores 4 hourly reactor temperature readings in Celsius as floating point values in a list. A list is useful here because the readings can be accessed and updated later, for example, if calibration changes are needed. A tuple is used to store the sampling port names because its contents cannot be changed after they are set. This makes it a good choice for fixed data that should stay constant throughout the program. The code first confirms that the temperature list and port tuple are long enough to access the needed positions safely. If they are, it retrieves the first temperature using the starting position and the last temperature using the final position in the list. You can access specific items in a tuple by their position. The second item gives the middle sampling port, while negative indexing lets you retrieve the final sampling port from the end without knowing the tuple's length. The code corrects the second hourly reactor temperature reading in Celsius. After calibration, the value is updated from 75.1 degrees to 75.4 degrees, making the recorded data more accurate. The code finds the overall temperature change by comparing the first and last recorded temperatures. This shows whether the temperature rose or fell over the period, and the result is saved for later analysis or reporting. The program prints selected values from a temperature list and a tuple of port names. It shows the first and last temperatures with their Celsius unit, prints the middle and final port names, then displays the corrected second temperature. Finally, it calculates the total temperature rise by comparing the last temperature with the first and rounds the result to 2 decimal places. The code finishes by reporting how many temperature readings are stored. It counts the items in the temperature list and prints that total with a clear message, giving the user a quick summary of the data size. This script shows how to work with sequence data using a list of reactor temperatures and a tuple of sampling port names. It checks sequence lengths before indexing, retrieves selected items such as first, last, and middle values, and updates one temperature after review. It also calculates the change from the first to the last reading and reports the total number of temperature measurements. Slicing sequences. Slicing selects a continuous portion of an ordered sequence, such as measurement data, without working with each item one by one. In chemical engineering, it helps isolate important ranges like startup or steady-state periods for analysis. Unlike indexing, which returns one value, slicing keeps the selected values in order, making trends easier to inspect, transform, and compare. When slicing a sequence, the start position is included, and the stop position comes just after the last item you want. This makes slice lengths predictable and lets adjacent slices connect cleanly without overlap. You can also slice from the end to focus on recent values, such as the latest pressure readings. Because lists and tuples keep their order, slicing preserves the logical or time-based structure of engineering data. Slicing is a key tool for preparing data, not just retrieving it. By isolating meaningful parts of a sequence, you can compare segments, calculate summaries, inspect results, or process the data further. This helps engineers focus on phases such as warm-up periods or stable operation, making raw data easier to understand and turn into useful insights. Python code slicing sequences. This section demonstrates how to slice ordered reactor measurements using small lists for clear results. It focuses on comparing process intervals directly without using loops, so the key slicing ideas remain simple and easy to follow. We organize the data with one list for minute labels from 0 to 5 and another for the matching Celsius temperature readings. This connects each measurement to its time point, making it easier to analyze temperature changes over time and select specific time periods when needed. Temperature list slices can separate the reactor's operation into phases. The first slice takes the initial startup readings, while the next slice captures later readings. This makes it easy to analyze each phase directly, without loops, keeping the code concise and readable. Use negative slicing to get the last 2 temperature readings without needing the list length. Then pair those readings with the matching minute labels using the zip function. The result is a set of minute and temperature pairs that makes recent data easy to review together. The startup temperatures are converted from Celsius to Fahrenheit by applying the standard conversion to each value in the list. Then, the recent temperatures are averaged by adding them together and dividing by how many values are included. This provides a concise view of the recent temperature trend. The output gives a concise overview of the temperature data by showing all Celsius readings, then separating the startup and later phases to reveal changes over time. It also highlights the most recent minute temperature pairs, converts the startup readings to Fahrenheit, and reports the recent average rounded to 2 decimal places. This script shows how to use list slicing with reactor temperature readings. It separates early startup temperatures from later readings, extracts the most recent measurements with their minute labels, and converts the startup values from Celsius to Fahrenheit. It also computes the average of the recent temperatures and prints the key results, including the original data, slices, paired recent readings, converted values, and rounded average. Looping through sequences. Looping through a sequence means visiting each item in order so the same action can be applied consistently. In chemical engineering, lists and tuples can store ordered measurements such as temperatures, pressures, or flow rates. Loops make it efficient to check limits, convert units, and process engineering data while preserving the order of the values. When looping through a sequence, decide whether you need each value, its position, or both. Values may be enough for simple calculations or checks, but positions matter when readings are tied to a time or location. Tracking both the item and its place preserves context and helps you report exactly when or where an unusual reading occurred. Loops let you transform sequences in a consistent order, which is essential for reliable data processing. They can be used to clean, scale, classify, or combine data while preserving integrity. By deciding whether to update a sequence or store transformed values separately, you can build reproducible workflows for engineering analysis. Python code, looping through sequences. Process the ordered reactor temperature data by moving through each measurement in sequence. Keep track of both the temperature values and their positions, and store any transformed results separately so the original data remains unchanged. We store hourly reactor temperatures in Celsius as an ordered list. This keeps each reading in its recorded sequence, making it possible to track changes over time and analyze or transform the data accurately. A safe reactor temperature limit is set at 90 degrees Celsius. This limit is used to flag any readings that go above it, helping ensure the reactor stays within safe operating conditions. First, create an empty list to hold the Fahrenheit temperatures. This gives the loop a place to store each converted value from the original Celsius data. We loop through the Celsius temperature readings and use the enumerate function to get both the hour index and the temperature value. This makes it easy to report and process each reading with its corresponding time. Each Celsius temperature is converted to Fahrenheit by multiplying by 9, dividing by 5, and adding 32. This changes the readings into the Fahrenheit scale, so both temperature units can be used as needed. The code adds each converted Fahrenheit temperature to a list in the same order as the original Celsius values. It rounds each result to one decimal place to keep the data consistent and easy to read. The code compares the current Celsius temperature with a safe limit. If the reading is above that limit, it flags the situation as potentially unsafe, so only temperatures over the threshold are reported for attention. This line alerts the user when a temperature reading is too high. It reports the hour of the reading and the temperature in Celsius, making it easier to spot possible reactor temperature control problems. This line displays the original Celsius temperature readings so you can review the raw data before conversion. It helps make the process clear by letting you compare the starting values with the Fahrenheit results that follow. We display the converted Fahrenheit temperatures so the transformed data is easy to review and compare with the original Celsius values. Printing the results makes the conversion clear and ready for later analysis or reporting. Use the max function to find the highest Celsius temperature in the list. This identifies the peak recorded temperature, which can then be printed with a clear message. The script reviews hourly reactor temperatures in Celsius, converts each reading to Fahrenheit, and keeps both sets of values. While processing, it flags any reading above the safe limit of 90 degrees Celsius by reporting the hour and temperature. It then displays the original readings, the converted values, and the highest Celsius temperature recorded. Sequence summaries. Sequence sums. In chemical engineering, sequence sums provide a quick way to total ordered measurements such as flow rates or temperatures stored in a list or tuple. A built-in summing operation can summarize the data without manual addition, supporting calculations like total solvent use or overall energy demand. This makes the data easier to interpret and use in later calculations. When summing a sequence, first ask whether the total has physical meaning. Quantities like kilograms of catalyst or liters of filtrate can naturally accumulate, but temperatures and concentrations usually require an average instead. A computer can add any values, but engineering judgment is needed to decide whether the result answers a meaningful question. Built-in sequence summation makes data analysis simpler, more reliable, and easier to repeat. For large sensor or lab datasets, it helps prevent missed, duplicated, or manually miscalculated values. Applying the same summing method across batches or experimental runs supports fair comparisons, such as tracking water use across production campaigns, and helps summarize performance and resource efficiency. Python code. Sequence sums. Sequence sums help summarize ordered engineering measurements, and a built-in sum reduces arithmetic errors. Engineers still need to decide whether the resulting total is meaningful for the problem. Store the solvent volumes from each cleaning interval in a list of floating point numbers. This keeps the measurements organized and makes it easy to calculate totals, such as the overall amount of solvent used across all intervals. A tuple is used to store 4 catalyst charge weights from different reactors, with each value representing kilograms of catalyst. Because tuples are immutable, they fit fixed recorded measurements and still allow the values to be accessed and added later to find the total catalyst used. The code first confirms that both the solvent and catalyst measurement sequences contain data. It checks that neither sequence is empty before allowing later calculations to continue. Use the built-in sum function to quickly total the solvent volumes and the catalyst charges. It adds all values in each collection, producing the overall solvent amount and total catalyst weight. These totals are simple, accurate, and useful for engineering analysis or reporting. A set of reactor temperature readings in Celsius is stored as a list of 4 decimal values. The average temperature is found by adding the readings and dividing by how many there are, giving a simple summary of the reactor's thermal conditions. The output summarizes sequence sums for a chemical engineering context. It first reports whether both measurement sequences contain data, then gives the total solvent used and total catalyst charged, each rounded to 1 decimal place. It also shows the average reactor temperature, with a note that the temperature sum is only used to compute the average and is not meant for final reporting. This script summarizes chemical engineering measurements by first checking whether solvent volume and catalyst charge data are available. It then totals the solvent used and catalyst charged and computes the average reactor temperature from the temperature measurements. The printed results report data availability, total solvent in liters, total catalyst in kilograms, and average temperature in degrees Celsius, with temperature totals used only to calculate the average. Mean measurements. Mean measurements summarize the central tendency of chemical engineering data, such as temperatures or flow rates, without reviewing every value. The mean is found by adding all measurements and dividing by how many there are. Built-in functions make this faster and more consistent, especially for long datasets or repeated experiments. When using a mean to summarize measurements, always connect the number to what the measurements represent. A mean can indicate whether conditions such as temperature, concentration, flow rate, or pH stayed near expected values, while reducing the effect of random variation. Built-in sequence operations help organize measurements, calculate totals, and interpret the result. And although order does not change the mean, keeping the order helps track where or when each measurement occurred. The mean is useful, but it can hide important variation, such as brief spikes or faulty measurements that distort the average. Always interpret the mean in context and compare it with other summaries when needed. Before calculating it, check that the data is valid and decide whether each measurement should have equal influence. Python code, mean measurements. Store reactor measurements in their correct order. Then use built-in tools to summarize the values. When reviewing the average, interpret it carefully so it reflects the data accurately. This comment explains that the script needs no extra package installation. It runs using only Python's built-in features, so it should work in any standard Python environment without additional setup. Temperature measurements are stored in a list of Celsius values. A list is useful because it keeps the measurements in order and makes them easy to access, change, or process one by one. Flow measurements are stored as a tuple of gallon per minute values. Because tuples cannot be changed after they are created, they help protect the integrity of the recorded data. The values stay in measurement order, making them easy to use later for calculations or comparisons such as averages or target checks. Use the length function on the temperature list to find how many measurements it contains. This count is needed to calculate the average because it tells us what to divide the total temperature sum by. We use the length function on the tuple of flow rates to find how many measurements are available. This count is needed to calculate the average flow rate correctly and avoid division errors. The temperature values are added together using the built-in sum function, and the result is stored as the total temperature. This total is needed to calculate the mean temperature, where it will be divided by the number of measurements. The flow measurements are added together using the built-in sum function. This total is then used to calculate the mean flow rate for comparison with the target conditions. The mean temperature is found by adding all the temperature readings and dividing by the total number of readings. This gives the average value, with each measurement counted equally. Mean flow is found by adding all the flow measurements together and dividing by the number of measurements. This gives the average flow rate, providing a representative value for the collected data. The reactor target temperature is set to 83 degrees Celsius. This target serves as a reference for comparing the reactor's calculated mean temperature, helping show how far the actual temperature is from the desired operating condition. The target flow rate is set to 15 gallons per minute. This value is used as a benchmark for comparing the system's average actual flow and checking whether it is operating within the desired range. The output summarizes the mean reactor temperature in degrees Celsius. The value is rounded to 2 decimal places, making the result precise, clear, and easy to read as an engineering summary. This line finds how far the mean temperature is from the target temperature. It rounds the difference to 2 decimal places and prints it as a temperature offset in degrees Celsius. This line reports the average cooling water flow rate, rounded to 2 decimal places for clarity. It also includes the unit gallons per minute, making the result easy to interpret as an engineering summary. This line shows how far the mean flow is from the target flow. It rounds the value to 2 decimal places and labels it in gallons per minute, so the output is clear and useful for engineering interpretation. The code reports the total number of measurements used in the analysis by adding the temperature readings and flow measurements together. This gives a quick sense of the dataset's overall size. This script calculates average reactor temperatures and cooling water flow rates from stored measurement data. It compares each average with its target value, prints the difference, and reports how many measurements were processed. The result gives a quick view of how current reactor conditions align with desired operating targets. Average measurements. Averages give a simple summary of repeated measurements, such as sensor readings in chemical engineering. Data like reactor temperatures or flow rates may be stored as sequences, and while individual values are useful for troubleshooting, the average shows the overall behavior in one number. Built-in tools can calculate this by combining the total of the measurements with how many readings were taken, such as finding the typical tray temperature in a distillation column. When averaging a sequence of data, first consider what the values represent and whether each one should count equally. A simple average is appropriate for regular, comparable measurements, such as readings taken at consistent time intervals. If measurements differ in duration, conditions, units, or sampling method, the average can be misleading. Use engineering judgment to ensure the data are comparable and the result is meaningful. Averages give a quick overview of data, but they can hide important variations such as spikes, drops, or samples outside acceptable limits. To judge safety, quality, and representativeness, Averages should be considered alongside summaries like minimums, maximums, and totals. Using built-in tools to summarize data helps turn raw sequences into useful engineering insight. Python code. Average measurements. Lists are useful for storing repeated process measurements, and averages help summarize typical operating behavior. Built-in tools make these simple summaries easier to read and use. Reactor temperature readings are stored in a list, so the data can be managed and updated easily. Each reading is a floating point value in degrees Celsius. This format supports later calculations, such as finding the average temperature to understand typical reactor conditions. Pipeline pressure readings are stored in a tuple because tuples hold an ordered sequence of values that should not change. This makes them useful for fixed data, such as pressure measurements recorded in pounds per square inch, or PSI, in the order they were taken. We use the length function to count the temperature readings in the reactor list and the pressure readings in the pipeline tuple. These counts tell us how many measurements are available and are needed later to calculate the averages. To find the average reactor temperature or pipeline pressure, add all the recorded values and divide by the number of readings. This simple arithmetic turns collected temperature and pressure data into meaningful averages in degrees Celsius and PSI. Create concise summaries for the average reactor temperature and pipeline pressure using formatted text. Each value is shown to 2 decimal places, making the results precise, readable, and easy to review. The output begins with a brief header, then reports the average reactor temperature and pipeline pressure, each rounded to 2 decimal places. It also shows how many temperature and pressure readings were used, giving helpful context for judging the reliability of the averages. This script summarizes reactor temperature and pipeline pressure readings by calculating their averages. It stores the measurements, divides each total by the number of readings, and prints concise results showing the average temperature in degrees Celsius, the average pressure in PSI, and how many readings were used. In this lecture, you learn to create lists and tuples to store ordered chemical engineering data, access and transform sequence elements using indexing, slicing, and loops, and summarize measurement sequences using built-in operations and functions. In the next lecture, Lecture B, we will go over dictionaries and files.
Thank you for your attention. See you all in the next lecture.